Alright, hi everyone, we'll be starting class in 1 minute time. Alright, good afternoon everyone, and today's lecture and tomorrow's lecture, or part of tomorrow's lecture, is going to be on the topic of stability. And in particular, we'll be looking at the use of the Routh-Hurwitz Criterion as to how can we determine if a system is stable or not in the Laplace domain. And we'll see in this lecture in particular, how do we formulate what we refer to as the characteristic equation using a system transfer function. And from that characteristic equation, we'll be using the coefficients within the equation itself to formulate the Routh-Hurwitz table and then solve and determine if the system is going to be stable or not. Now, one thing to note before we start this lecture, the use of the Routh-Hurwitz criterion, or the Routh-Hurwitz table here, only tells you if the system is stable or not, and it will tell you how many poles are on the left-hand side of the S-plane or on the right-hand side of the S-plane. It does not tell you the actual location of the poles. That's all the Routh-Hurwitz table can tell you, if the system is stable or not, and how many of those poles are going to be on the left-hand side of the S-plane or on the right-hand side of the S-plane. Cannot tell you the actual location of the poles themselves. Alright, so let's start this lecture. So, in general, when you deal with any stable system, it basically means that for every bounded output that you have for that system, there must be a bounded input. And in particular, that means that the Laplace transform and the inverse Laplace transform of that equation must exist. So we can have a y of s equation here that can be in the up to order 2 on the denominator and order 1 in the numerator here. And we know basically once we deal with the Laplace transform to get it back into the time domain, we basically do partial fractions and then use the Laplace transform table to obtain the inverse Laplace transform and get the y of t equivalent here. What you may not have noticed, on the other hand, though, and which was briefly touched upon in the pole zero lecture that was like at the start of the semester, is that depending on the factors here on the denominator, which we refer to as poles, this will actually help you determine the stability of the system. And when we talk about the poles being on the left-hand side of the S-plane, that means these poles here are going to take a negative value, because this is like if we take s plus 3 here is equal to 0, so that means s is equal to negative 3. And similarly, if we take s plus 2 here is equal to 0, that's going to be s equals to negative 2. And because those s values there are negative, meaning that they are less than s equals 0, that means the system itself is stable. If those s values were positive, so let's say if this was s minus 3 and s minus 2, those poles will now lie on the right-hand side of the S-plane, meaning that it's going to be s more than 0, and as of such, the system is going to be unstable. So, in particular, when you're determining the stability of a system, it's very helpful if you actually have the poles of the system in a factorized form from this system equation. And you can immediately tell once you do this factorization here that if the system is stable or not by seeing if these s values here for the poles are going to be negative in particular. And similarly, once you have it in the time domain, this y of t here, if you have negative exponents, this means that your system here is going to be stable. If you have positive exponents on your hand, that means your system is going to be unstable. So, like I said, notice that the poles of y of s here are on the left-hand side of the s-plane, meaning s less than 0. And for any stable system, that means your poles here need to have negative real parts as of such. Otherwise, your system is going to be unstable. And this also holds true for complex poles, because even if you have a positive imaginary part here, but the real part here is negative, that still means that the system is going to be stable regardless, because it's going to lie on the left-hand side of the s-plane. Being at s equals to -3 on the left-hand side, so that's s less than 0. And the 2j here, because the axes are imaginary versus real, that just determines the vertical transition of that pole in particular. But in general, it's still going to be on the left-hand side of the s-plane. So our good idea here is that we will have some 0 here for our example equation, but then we have our poles here represented by x's, and these are complex poles, because we see here that the real part here is at -1, but then the complex part here is at 2j and -2j. But because it's still less than s equal to 0, in particular, the system here is perfectly stable. And even though if this 0 value here was on the right-hand side, we only care about the poles in particular. So those pole values, once they're less than s equals to 0, that means your system is stable no matter what. So typically when you're dealing with like systems that are like up to the power of 2 or power of 3 and so forth, it's really easy to find the roots of these systems and determine if the system is stable just by observation. But if you start getting like some complex questions in particular, this isn't so easy to observe, especially when you start going up into like powers of 4 and 5 and so forth. So there's got to be a more optimal way in order to determine if a system is stable or not, and then how many poles are going to be on the left-hand side or on the right-hand side of the s-plane. So given this particular question here, we see that we have a k component here that can assume any value. And because of this k component, that means we're going to have to figure out what's going to be the range of k here for which the system here will be unstable, as our question asks. But before we do that, the first part of the question basically asks you to find the closed-loop transfer function, which is absolutely required because we need to start this with the overall system equation, mapping y of s here being our output and our input here x of s. So typically it's possible to obtain the transfer function here because this is just a closed loop negative feedback system, where this block here will represent our g of s and this block here will represent our h of s. And we know from our previous lectures for a negative feedback system that the system transfer function is of the form g divided by 1 plus g h of s. And after we obtain that transfer function, we can then observe the behavior of the poles with respect to k and then solve for that range of k, which makes the system unstable. But that tends to be like already tedious and so forth, because now that means you're going to have to factor in that k factor here with all your poles and so forth. And that tends to take very long, especially when you start dealing with more complex systems. So the efficient way to actually go about doing this is using the technique known as the Routh-Hurwitz Stability Criterion. And that's what we're going to be focusing on in today's lecture, as to how do we use this criterion in particular to determine stability of the system and how many poles lie on the left-hand side of the s-plane or the right-hand side of the s-plane. So, as I mentioned before, the first step is that you need to have the system transfer function itself, meaning that you need to have y of s divided by x of s here, our outputs divided by our inputs. And because we had our closed-loop negative feedback system, this is the reference equation for that closed-loop negative feedback system here. And then once we obtain this general equation for our system here, we then watch the denominator of that transfer function. And watching the denominator of that transfer function, we equate it to 0 and refer to this as our characteristic equation of that transfer function. So we need to obtain the characteristic equation, being that once we obtain our system transfer function mapping the output here y of s to our input x of s, we then take the denominator of that transfer function and we equate it to 0, and that is going to be our characteristic equation of the transfer function. Typically, once we have this characteristic equation being equated to 0, we tend to need to make sure that it's going to be in descending polynomial form, meaning that we start with the highest power of s, and then we go to the next highest power, and we go on all the way down to s to the power 0 in particular. So it's no good if this equation here is in factorized form. You need to actually multiply this out and get it in descending powers of s here before we can proceed with the Routh-Hurwitz criterion. Once we have that descending powers of s form for our characteristic equation, we can then tabulate the coefficients into the Routh-Hurwitz table as follows. Now, in this particular case, we see here that the highest power of s here is an even power. So that means the first row of our table here will be coefficients of even powers of s, meaning that this would be s to the power 4 coefficient, and the next one here is going to be s squared coefficient, and then the next one here is going to be s to the 0 coefficient. And then the next row of the table would then go to the next highest power of s here, which is going to be s cubed. In this case, it's going to be odd power of s. And as of such, then we tabulate all the coefficients of the odd powers of s here onto the next row. So this is going to be the coefficient of s cubed, this is going to be the coefficient of s to the power 1, and if it did exist here, this would be the coefficient of s to the negative 1. But because it doesn't exist here, this coefficient here is just going to be 0. So as of such, when we formulate our table here, and like I said, we started with the highest power of s, and we observed that was even, so that means we will be taking the even the coefficients of the even powers of s. That means that the s to the 4 coefficient here was 1. The next coefficient here is going to be s squared, which is going to be 3. And then the next coefficient here is going to be the s to the power 0, being our constant coefficient, which is going to be 5. The next row here is going to be the odd powers of s, and this will be related to the coefficients of the odd powers of s. So that means for s cubed, that coefficient here is going to be 2. For s to the power 1 here, that coefficient here is going to be 4. And because there isn't a s to the negative 1 power, that means that the coefficient there is just going to be 0 accordingly. The next step is to actually complete the Routh-Hurwitz table doing a series of calculations as we keep on going. And these calculations repeat out throughout the entire table. So if you notice here in particular, from this general equation that we're seeing here in the green highlighted block, we can see that in doing the calculation for this, there's basically a cross multiplication going from this direction here, and then this direction here, and then you divide by this coefficient here in particular. So, in watching it, map into what we just drew here on the slide, an minus 1 and an minus 2 here is just a cross multiplication here. And then we minus the next cross multiplication, which is going to be an minus 3 by a to the n here. And then we divide by our start point here, which is going to be an minus 1. First part of the criterion. Okay, yeah, sure. I'll go back to that. So the first part of the criterion is that you need to obtain your transfer function for your system, meaning that you need to get y of s divided by x of s here for your entire transfer function for this entire system. Once you obtain your transfer function or your system transfer function as such for the entire system, you then take the denominator here for that transfer function and you equate that to 0. That's going to reflect this, that's going to be your characteristic equation here. So you obtain your system transfer function, which is y of s divided by x of s. You then take the denominator of this transfer function and you equate it to 0, and that's what's going to be your characteristic equation as of such. Once you obtain your characteristic equation, it needs to be in descending powers of s. So you start with the highest power of s, and then you go to the next highest power and so forth, and all the way down to the lowest power of s possible. this characteristic equation is no good if it is in factorized form. It needs to be expanded out and in descending powers of s accordingly. And you're equating this entire characteristic equation here to 0. The next step, once you have your characteristic equation, is to formulate the Routh-Hurwitz table. In formulating the Routh-Hurwitz table, you see what is the highest power of s and determine if it's odd or even. For example equation here, the highest power of s contains an even power. So the first row of this table here will start with coefficients of even powers of s. So because this first row here is going to be an even power, we start with the highest power possible, that is even, so that's s to the 4 here. We observe the coefficient for s to the 4, which is going to be 1, and we map that into our table here. The next coefficient here, which is also going to be an even power of s, is going to be s squared. So we then watch what's the coefficient for s squared here, and in this case it's going to be 3. The next coefficient here, because this is only even powers of s we're dealing with, is going to be s to the 0. So that's going to be 5 here. The next row in the Routh-Hurwitz table will deal with the next highest power of s in the entire equation. So in this case, this is going to be our even coefficient. Sorry, we dealt with our even coefficients in the first row. Now we're going to be dealing with our odd coefficients here in particular. So these coefficients are going to be mapped to the odd powers of s that exist in our equation. So that means the highest odd power of s here is going to be s cubed. The coefficient in front of s cubed here is going to be 2, so we map that into our table. The next odd power of s that we have in our equation here is going to be s to the power 1, and the coefficient in front of that is just going to be 4. The next possible coefficient here that we map into the next odd power of s would have been s to the negative 1, but that s to the negative 1 doesn't exist in our equation, so we just put a 0 here mapping that coefficient. To give you another example, so let's say we have an example equation here. Example characteristic equation being s to the 5 plus 2 s to the 4 plus 3s cubed plus 6s squared plus 5s plus 1. If we had to do our Routh-Hurwitz table here for this, in particular, we'll start with the highest power of s here and drafting our Routh-Hurwitz table. So that's the first step in drafting the Routh-Hurwitz table from the characteristic equation. You watch what is the highest power of s in your entire characteristic equation. And we see here that the highest power of s is going to be an odd power. That means when we do our Routh-Hurwitz table, we want to start with only odd powers of s for our first row. So that means you'll start with s to the 5 here. So we then watch what's going to be our coefficients here for s to the 5, and then the coefficient for s cubed and the coefficient for s to the power 1. Because the highest power of s here is odd, so we're going to be dealing with only the coefficients of the odd powers of s. So s to the 5 here means the coefficient here is just going to be 1. The next highest odd power of s that exists in our equation is s cubed. So the coefficient here is just going to be 3. And then similarly, the next highest power of s that's odd here is s to the 1. The coefficient here is going to be 5. So that deals with all the coefficients of the odd powers of s. The next row here, because we dealt with the odd powers of s, is going to be the even powers of s. And then the highest even power of s here is s to the 4. So we start with s to the 4 here being the highest even power of s, and we see its coefficient here is going to be 2. And then the next highest even power of s here is going to be s squared, so that next coefficient here is going to be 6. And then the next highest even power of s is going to be s to the 0, so that's going to be a coefficient here of 1. So depending on what's the highest power of S, and if it's even or odd, that determines how do you start your table, and then the next row is just going to be the next set of powers in particular. So for our equation here in the yellow highlighted region, the highest power of S here was even, so that means our first row here will only be dealing with coefficients of even powers of S. The next row here will deal with odd powers of S and their respective coefficients. For this example equation that I wrote out here, the highest power of S here is odd, so that means the first row here will only be dealing with coefficients of odd powers of S. And then the next row here will be dealing with coefficients of even powers of S in particular. But once we have those first two rows, we then need to do a series of repeated calculations throughout the entire table to fill in the other rows as we keep on going down to the S to the 0 row for the Routh-Hurwitz table. So the calculation basically follows such that it does a cross multiplication. We don't start with the top left, we start with the bottom left for that cross multiplication. So we start with a to the n minus 1 here, and we cross multiply accordingly. So that means a n minus 1 here needs to multiply by a n minus 2. And then for the next part of the cross multiplication, this is going to be a minus. So the next part of the cross multiplication will be a n minus 3 multiplied by a to the n. So a to the n here and a n minus 3 multiplied by each other. And that's going to be a minus in particular. The last part of the equation means that you're going to be dividing by the start point of your cross multiplication, which is going to be a n minus 1 here. And this polynomial theory is also referred to as Sturm's theorem. So in doing this cross multiplication and this division here, we obtain the next value for our next row of the Routh-Hurwitz table. And we keep on doing this in particular to fill in these rows until we get to the S to the 0 row for our Routh-Hurwitz table. And yes, it looks a little bit confusing because we're watching this in symbology terms. But once we actually watch this with respect to our example equation, it's going to be a lot more clearer as to how we keep on doing these repeated calculations. Similarly, when we move to the next available value here to calculate for our next row in our Routh-Hurwitz table, because we're dealing with this value, we hold these first two values here constant, and then we shift the next two values here to the next possible two values in these first two rows. So the cross multiplication basically is going to be the same. But we have a to the n minus 1 here multiplying by a to the n minus 4, as we see in our equation. And then we have a to the n here multiplying by a to the n minus 5. And we still divide by our start point here accordingly as of such. So let's actually do this in practice here with our example equation, which we started off with. And this example equation here being our characteristic equation of our system. So the table here is basically completed, but I'm going to do the calculations here on the slide here to show you how we went about calculating these. So our first value here for our S squared row, because as you can see here, as we're going to be completing our Routh-Hurwitz table, each one of these rows, we start with the S to the power 4 row and the S to the cube row here. We keep on going down in powers of S here and filling in these values as we go about doing our Routh-Hurwitz calculations. So we keep on going down in particular until we hit our S to the 0 row, and then we stop, and then we determine if our system is stable or not by watching a few observations regards to this table, which we're going to see in the next few slides. But for now, we're going to be focusing on how do we go about doing our Routh-Hurwitz calculations in particular. So for the first value here, for S squared row, which is what we're going to need to calculate for, that's going to be the cross multiplication of these two values here, and then these two values, and we're going to be dividing by this 2 value here, which we started on cross multiply. So let's actually watch that calculation. So that's going to be, we're going 2 by 3 minus 4 by 1, and then we need to start, we have to divide by our start point, which is going to be 2, and that's going to be 6 minus 4 divided by 2 gives us a value of 1. So that maps our value here of 1 accordingly. Let me rub that off, and let's do it for the next value that we're going to be calculating for in the S square row. So we're going to be watching in particular for this value here as to how do we determine this value for our S squared row. So in calculating for that value, remember we're going to be holding these two coefficients here, constant. But instead of using these two that we did when we calculated for 1 here, we're going to be using these two instead to obtain this value here. And in doing so, when we do the cross multiplication, we go from there and here, and we're going to be dividing by our start value. So that's going to be 2 multiplied by 5 minus 0 by 1. And we're going to be dividing by 2. And this 0 by 1 here just going to give us 0. This 2 multiplied by 5 here, we can see the 2 is basically cancelled, so that's going to be 1 and 1, which will give us a resultant value of 5, as we can see here in our table. So, as we notice in our table, we extracted the coefficients for S4 and SQ here from our equation, and then we calculated for coefficients here for S squared. But we note that there's still going to be an S to the 1 row here and the S to the 0 row, so that means these calculations need to continue in some form or fashion. So in continuing these calculations, we do the same thing, but then we just drop down by 1 row, because we're only going to be dealing with 4 values at a time. So the calculations basically follow the same method that we just now saw for the other rows. But that means that we're just going to be dropping down by 1 row each time as we keep on doing our calculations. And the cross multiplication here is basically the same. So you can see here b n minus 1 and a n minus 3 multiply by each other. And then b n minus 3 and a n minus 1 multiply by each other. And we divide by our new start point here, which is going to be b n minus 1 in particular. And that determines our Cn-1 value, which in our practical example, that's going to be the values here for s to the power 1. So let's actually see how we determine these values in particular. So this s to the 1 value here that we're going to be calculating for, we're only going to be dealing with 4 values at a time. Because we already dealt with the s square row and we're going to the s1 row, that means we're going to be using the 2 values right above it here, and then the next 2 values here accordingly in order to solve it. And if we do a cross multiplication using those values, that's going to be 1 by 5 minus 4 by 2, and we're going to be dividing by our start point, which is going to be 1, which is going to be 5 minus 8 divided by 1. No, sorry, I did that wrong. And I'll watch back my equation here, and I wrote that equation entirely wrong. Apologies. That's going to be, so if we watch our cross multiplication here, it's going to be 1 by 4 minus 5 by 2. And we're going to be dividing here by 1. So that's going to be 4 minus 10 divided by 1, which is going to give us a value here of minus 6. You can see. Similarly, someone's going to ask me, well, okay, what about this value here? Because we have these 2 values here, and we had a 0 value here, but we didn't have another value here in particular because we didn't calculate for it. And the reason why we didn't calculate for this value is that, I clear the ink on the slide here to explain why we didn't calculate for that value. And we need to find this value here. that means we need to start with these two values here, and then we need to have two values here existing in order to solve it. And because these two values here don't exist, that means it's just going to be zeros here in particular. That comes like we have 2 by 0 here. Then we have 1 by 0, and we just divide by 2, which is just going to give us a value of 0. So that's why we leave it blank. Similarly, if we're trying to solve for this value here, that means we're going to be dealing with these two values here, and we're going to be dealing with these two values here as well. And because this value here is blank, that's just going to be 0. So if we did a cross multiplication here, that's going to be 1 by 0 minus 0 by 2. And if we divide by our start point here, which is going to be 1, the numerator here is just going to be 0 divided by 1, which is going to give us a value of 0. And that's why we don't really bother to calculate fit, because we know that it's just going to be 0 regardless. And then, because we have our s to the minus 1 coefficient here, our last step here is to get our s to the 0 coefficient. And we're calculating for this here, we're going to be using the two values right above it, and then these two values here. And because this here is blank, that's just going to be 0. So if we cross multiply here, that's going to be minus 6 by 5 minus 0 by 1, and we're going to be divided by our start point here, which is minus 6. So this 0 by 1 here is just going to be 0. That minus 6 and minus 6 here will just cancel, so that's going to be 1 and 1 here. And 1 by 5 here is just going to give us a value of 5. You can see here in our table itself. At that point, the Routh-Hurwitz table is basically completed. So it's just basically a series of repeated calculations that you keep on doing for your Routh-Hurwitz table. And as you keep on going throughout the entire thing, remember you're only going to be dealing with 4 values at a time. So if we'll calculate for this one value here, we'll be dealing with these first 2 values and then these 2 values here in particular. If we calculate for this 5 value here, we'll be dealing with these first 2 values, which will remain constant throughout. And then we'll be dealing with these next 2 values here, in particular in the rows above them. When we move to the s to the 1 row here, we'll be dealing with these 2 values right above it, and then these next 2 values here in order to calculate for this value. And then similarly for the s to the 0 row, we'll be dealing with the 2 values right above it, and then the next 2 values accordingly next to it. And it's basically just a series of repeated calculations that you keep on going on until you obtain down to the s to the 0 row. And at that point, the Routh-Hurwitz table is completed. Once the table is completed, it's just basically to do a series of observations with respect to the table to determine if the system is stable or not. And in particular, the first rule here basically tells you is that for your system, the elements in the first column here of your table must be strictly positive, meaning that they must be more than 0. And once this condition is fulfilled, your system is basically going to be stable. If this condition here is violated in any form or fashion, that means your system is going to be unstable. So for our example here, which we just now did, and we completed our Routh-Hurwitz table, we see here that for our first column, we need to observe how many sign changes is there going to be in particular. And the reason why we observe the sign changes is going to help us determine how many poles are going to lie on the left-hand side and the right-hand side of the S-plane. Now, we can immediately observe here in our first column that all the values here are not strictly positive, so we know our system here is going to be unstable. But in observing how many sign changes occurred in our first column here, we see that from here to here, from S4 and S cubed, there's no sign change, so that's perfectly alright. And then from here to here, it's still positive between the 2 values, so that's perfectly alright as well. However, when we go from here to here, meaning S squared and S1, there is a sign change. I'm just going to call that SC here for the time being. And then when we jump from -6 positive 5 here, raise this. When we jump from -6 to positive 5 here, we also have another sign change here from negative to positive. That's also another sign change. So, in answering the question, we have two sign changes in particular. And those two sign changes occurred when we went from, those two sign changes occurred when we went from a positive value here of 1 to a negative value here of -6, so that was our first sign change. And then we had another sign change where we went from -6 here to positive 5. So as of such, we had two sign changes accordingly. And because we had two sign changes, that's going to determine the number of roots of the characteristic equation with positive real parts. And what that means is that doing so, the number of sign changes here will tell us how many poles, or how many roots in this particular case, you can refer to it as either one, are going to be lying on the left-hand side of, on the right-hand side of our S-plane. So if there were no sign changes here, that means all the poles are going to lie on the left-hand side of the S-plane. Oh wait, no, sorry, I said the wrong thing. Let me clarify that. The number of sign changes refer to the number of poles that are going to be on the left-hand side of the S-plane. My apologies. So if there are no sign changes, that means all the poles lie on the left-hand side of the S-plane. But if there are, depending on the amount of sign changes that occur here, that's going to determine how many poles are going to lie onto the left-hand side of the S-plane in particular. So in this particular case, you can see here that because we had two sign changes, that's going to be two poles lying on the left-hand side of the S-plane here, meaning for S less than 0. And then the other two poles here are going to be on the right-hand side of the S-plane, meaning S more than 0 accordingly. And if we solve for the roots of these equations here, for this particular equation, we can see here that we see where our poles are physically located as of such. Now remember, the Routh-Hurwitz table can only tell you if the system is stable and how many poles lie onto the left-hand side of the S-plane accordingly. It cannot tell you where the physical location is, and in order to obtain the physical location, that means you need to solve for the roots of this characteristic equation as of such. Alright, so that basically brings us to the end of our stability lecture for today. And basically what we observed is that we need to obtain our system transfer function mapping our outputs or inputs. Then we take the denominator of that system transfer function and we equate it to 0. And that is going to be our characteristic equation. We need to expand out our characteristic equation and make sure that it is in descending powers of S in order to form our Routh-Hurwitz table accordingly. We then, in forming the Routh-Hurwitz table, we observe that in obtaining the first two rows of the table, we need to know what's going to be the highest power of S that exists within our characteristic equation. And if, let's say, for our particular example here, the highest power S was even, that means we're going to be dealing with coefficients of even powers of S first, and then the next row will be coefficients of odd powers of S accordingly. We see that once we've filled in those first two rows, we then need to fill in the other rows of the Routh-Hurwitz table, because that will give us the S to the power 4 row and then the S cube row. Then we want to be calculating for coefficients for the S squared, the S1, and then the S naught row. And we basically saw from the slides that it's basically a series of cross multiplications that keeps on repeating themselves until we get to the S to the 0 row. Once the Routh-Hurwitz table has been completed, we then observe all the elements in the first column of the table, and if they are strictly positive, meaning that they are more than 0, that means your system is stable. If there are any sign changes, meaning that if any of those values there were negative, that means your system is unstable, and the number of sign changes you observe in that first column determines how many poles lie on the left-hand side of the S-plane. Now, in doing the Routh-Hurwitz calculations in particular, and in preparation for these kind of questions, the only way that you can actually familiarize yourself with this is by actually attempting questions themselves with the Routh-Hurwitz Criterion table. And as you keep on doing and repeating questions for this particular topic, you basically tend to see that it's basically a series of repeated calculations as of such. And once you familiarize yourself with the repeated calculations, it becomes a lot easier to discern how do you go about doing the calculations and formulating the table and seeing how the calculations repeat themselves as you keep on calculating for coefficients in the rows afterwards as you descend to the s to the 0th row. So the only way to actually familiarize yourself with this kind of question is to keep on practicing it in particular. Are there any particular questions or anything that anyone is unclear about with regards to what we've seen in today's lecture so far? All right, doesn't seem like we have any questions at this point in time, so if there are any questions, please feel free to leave them down in the comments below, or you can email me directly and I'll answer you guys accordingly as such. For tomorrow's lecture, we'll be focusing on special properties of the Routh-Hurwitz table, and these properties are important because they deal with certain conditions that you may observe while you're actually doing the calculations within the Routh-Hurwitz table. And as of such, they are very helpful as to how do you continue the Routh-Hurwitz table when you encounter such conditions. Once we finish that particular topic tomorrow, the last lecture we're going to be doing tomorrow is the introduction to discrete time system. And that is going to be quite important for next week's lectures, which is going to be the Z transform. And Z transform is useful for discrete time systems. And in particular, the reason why this is so, that the Laplace transform is useful for continuous time systems, but you cannot apply the Laplace transform to a discrete time system. As such, you need a new transform known as the Z transform. However, when we start on that topic, you're going to basically see that the similarities between the Laplace and Z transform is going to be very similar. The only key difference is that you're going to just have to figure out how to use the Z transform table when we're doing that topic. All right, so tomorrow's lecture, like I said, is going to be where we're going to complete on the topic of stability and the special conditions for the Routh-Hurwitz table, and then we'll be doing the introduction to discrete time systems in particular. So try your best not to miss tomorrow's lecture because those special properties tend to be tested upon quite regularly in your final exam for the Routh-Hurwitz questions in particular. So until then, take care, be safe, and I will see you guys soon. Later.